version, I'm going to take the advanced version. You can't make a mistake on understanding which is which because it says under it, it says at the top of it that this is the advanced and it says these are the standard, and there's two sets of questions that are almost identical looking, but they're not identical in flavor. The advanced stuff has advanced homework that goes along with it. So I will look at that kind of homework. Of course, when you're on an advanced track, you're not doing exactly the same homework problems on quizzes. You're actually doing something more than that. So again, there are some of you who had really solid undergraduate abstract algebra courses at terrific places. If you want to do that, I think that's great because I don't want to do a disservice to you. Standard track, don't feel like, oh, well, this is the standard track. I am picking the problems as you're going to see today. We're not just covering freely and going, oh, here's the theorem number 5, I'm going to cover theorem number 5 for you. That's what you do when you're an undergrad. What I'm doing is trying to give you more exploratory problems to think about, having you think more deeply about it. You're not getting assigned problems 1 through 6, you're only getting assigned problems 56, for example. So it's not the same track at all as an undergrad track, at least here. Depends where you go. So again, with the advanced track, your learning is going to be more self-directed. So it's not going to be like I can cover everything to 2 different lectures in class. That's not going to always happen. So right now we're covering permutations, but we're going to be deviating quite a bit from Fraley because I want to give you more deep understanding what permutations are, and I've been building up to use the dihedral group as an exploratory vehicle for this section. So there's a reason, a method to my madness. So today's homework will all come from the notes. You'll see it in the pieces of the notes. So if you want to get a book, I wish I actually had got this book. I was looking for something like this prior to teaching the class because I have this issue, like where is Montclair State's graduate program? Where do we fit? Because we're not at Georgia Tech and taking a book from Georgia Tech and using that. That would crush anybody. But we need something that's right at our level where we can actually do a day job and come here at night and think, but beyond something at the undergraduate level. And if I had known about this book, I would have chosen this book. You're welcome to get it and take a look at it. It's terrific, actually, because it lays everything out. It's not a, I don't know if any of you used Ken Bogart's book for combinatorics, but that one's all hands-on. It's not all hands-on. It has some solid exercises, has a structure to it, then it has some activities in there where you can get to know the material better. And so that's kind of what I'm following now. Some deviations from that. So what are the focus questions that I'm looking at in this particular lecture? Well, the first is, how can we describe the symmetries of a regular polygon? We already have talked about this, where I showed you the triangle and we rotated it and we looked at the actual Cayley table, and we did it with the dihedral group of 4, where we looked at the square and we looked at all the possible symmetries of the square and we created the table. But after some time, like, what if I gave you the octagon and asked you to find all symmetries of the octagon? You'd probably key my car, because that's going to be a horrible exercise, right? You have to sit there and figure out all the symmetries and make sure you got them all, do you have them all? So this is one of the things I'd like to do, is characterize it for all n. Some simple way to think about the symmetries of an n-gon all in one shot. Generalize that idea so that you don't actually have to take one by one and start rotating it and looking at the symmetries and then writing out the Cayley table. So what are the dihedral groups and what are some of those important properties? Why am I talking about it? Why does Gallian talk about it so much? Why are they kind of the motivation for abstract algebra? They are. What are the generators and relationships that we see in those groups, and how can they be used to describe the group structure? And from this lecture, you're going to get a definition of something called a presentation, and that's an extension of what we know as a cyclic group. So that's what I mean by deeper. We're going to learn a little bit more. We're going to actually take what we know about cyclic groups, merge it with permutations, and extend it. So I'm sticking with the notation today. The dihedral group of a triangle, I have D3. The R1 and R2 represented rotations, and the little r1 and little r2 and little r3 represents reflection. So I'm going to stick with that instead of going to Fraley, because I think Fraley's is a little bit confusing and it doesn't actually work with what we're trying to do today. So what I'd like you to do for the first set of homework, you can scribble it down if you want. So answer whether the following is a rotation or reflection of D3. So if I take in two arbitrary rotations and I compose them together, is the result going to be a rotation, or is the result going to be a reflection? Is the composition of a rotation and a reflection, is that going to be a rotation or a reflection? And the composition of two reflections. So what I recommend doing is actually cutting out a triangle, moving it around so you can see it, and then folding it up along its vertices, because it'll make it a lot easier if you're just rotating it around and looking at it. I had seen a high school student look at all kinds of, he was looking at algebraic topology of of shapes, three-dimensional shapes, and amazing kid. But he had built his own little structures, and he would give his talks and present with those structures, so you could see what he was talking about when he talked about the symmetries. It just makes a difference. And of course, these PowerPoints will be up online too, so you can go back through it and find it. But you might want it in your notes too. Something always seems to happen when you can't download the PowerPoint when you need it. Canvas goes down. That'll happen. Got it all? Robert, need a couple more minutes?
I got it.
Okay. And which elements in D3, so that's the triangle again, in the Cayley table, which elements can be expressed as taking a reflection, taking the rotation, the first rotation, like the first one, and raising that to a power and multiplying or composing it with the first reflection, or a power of it. So you really will go dig into that table and play around. I'm calling this all the time mathematical play because that's what it feels like to me. And again, as an undergrad and a beginning grad student, I used to think that was a waste of time. I used to always think, this is a waste of time. I just need to get the proof done. But I didn't understand how important that was, contributing to my strength of the thinking this way. So how I think that had to change. And I didn't get it. I actually remember, I was telling someone on the phone today, I actually remember my honors calculus professor trying to help me in linear algebra. I had some crazy linear algebra teacher. I had a crazy linear algebra teacher who gave all proofs all semester long, nothing else. Didn't get it. Said, go to her for help, and she'd say, write down the definition. What is it you know? I'd look at her blankly thinking, why is she wasting my time? I need to solve the proof. So I just didn't get it. I remember feeling that way. So final problem, I think this is no, you got more. So if t is an integer, can you take r1 to the t, r1, and rewrite it as r1 times r1 to the j for some j? So you're really, again, going to dig into that Cayley table and see if some of these things can be done. If so, what's going to be the formula for the j? So what I would mean there is that you fix the t, like take t to be 2. Can you find the j? Can you find a pattern of what the j is going to be once this guy is known? And 6 is the punchline. The answer to all of these are yes, 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 yes. But you have to find it and actually show it. But the final thing is that if you set r to be r1, because you don't need a subscript anymore, and you set capital R to be r1, you can rewrite the entire Cayley table for D3 so that every element is in the form of powers of little r composed with powers of big R. And that's really important because it's telling you that you only need to know stuff about little r and big R, and everything else follows after that. You can kind of feel it when you're playing at your desk and you're writing your table out. You're like, oh, I kind of did this already. When you're filling out the Cayley table or you're doing some computation, you felt like, oh yeah, that was the same thing I did when I reflected this way. It feels the same way. I just have a different letter that I'm using. So it should make sense as you're doing this. Okay, any questions? By the way, this little diagram down at the bottom is an example of permutations. You're permuting the different colors.
This is not on the exam, it's going to be on the quiz next week?
Yes. Yeah, that's the bad part of having the exam Wednesday. I have to move on or else I won't, cover the topics that are listed on the comprehensive exams. So what if I have a polygon with more than n equals 3 sides? N equals 4 was doable. Well, first of all, I would like to know how big my Cayley table is, so I can spite the teacher if they ask me to figure out what the octagon is. How many am I going to get in that little Cayley table? The answer is I'm going to have at most 2n symmetries of the n-gon. And in fact, so let's look at that first. Why will you have no more than 2n? So you can only hate your teacher no more than 2n. So if you have n equals 8, for example, you have 16 elements in there, right? So I hate you for giving me a 16 by 16 Cayley table. You have to specify the hate. So why is this true? Be specific with the hatred. So take, for example, I've started something that looks like the start of some crazy octagon, or I could make it worse looking. But I'm going to have these vertices that are going to go through, and you start counting where something can get sent to. So vertex number 1, where can it be sent to? Well, it can be sent at most to and other places, right? Itself and then back to it, right, itself. So the vertex 2, if I want it to get some independent, it's sent to an image that's adjacent to a vertex of 1, right? It's always got to be next to the vertex of 1. So there's really only 2 extra choices for 2. From probability class, you already know what to do when you count all the first choices and then you count all the second choices. How do you get all the choices? Remember multiplication? You multiply them together. So that gives you 2n at most choices. So can we have less than 2n? Did something ever fall short? We know at most we can have 2n by this stupid argument of how many possibilities could there be where 1 gets sent to? How many possibilities could there be where 2 gets sent to? Multiply them together, it gives you 2n. Can there be anything less than 2n? Did something fall short? Well, the answer is no. And you can actually count them and show that you get exactly 2n. I'm not going to do that here. But so the hatred is specifically going to be 2n. So if I gave you n equals 16, that's busy work, right? You have to fill out the Cayley table for a 16 by 16 thing. So the symmetries of the Dn are often called the dihedral group of order 2n. And it's called order 2n because order also stands for how many elements there are in the group, which I think everybody in here has covered in their undergrad abstract class. And Fraley also defines it. The order of a group is the number of elements in that group.